Hello, class. In this video, we're going to be talking about solving higher order polynomial equations. These are going to be a natural extension of the techniques that we use to solve things like linear and quadratic equations, since those do represent what you might think of as lower order polynomial equations themselves. So let's get into it. Okay. A higher order polynomial equation refers to the degree of the polynomial. So as we mentioned in class, whenever we're solving a linear equation, we can think of that equation as a degree one polynomial because the standard form of a a linear equation is ax plus b equals 0. You might remember from your grade school days, mx plus b equals 0. Okay, but the a and the b just represent numbers that will change from problem to problem. And the degree of the polynomial equation can be determined by looking at the highest exponent that's represented or attached to the variable x or whatever the variable happens to be. Okay, so in contrast, a quadratic equation is a degree 2 polynomial because it's usually written in the form ax squared plus bx plus c equals 0, where x to the second power, that second power, it tells us what our degree of the polynomial is. So in this section, we're going to be talking about higher order polynomials. And the ones that we encounter in our class are going to just be degree 3, which can be called cubic polynomials, and degree 4, which can be called quartic polynomial equations. Okay, so diving right in, if we needed to solve a cubic polynomial equation, we might think that this is a new type of thing that we've never seen before. We don't know how to deal with the third power here on the x. But actually, we've learned a few techniques in previous lectures that are going to help us out here. For one, if you think about um, one idea that we learned in a previous lecture, and that is if we have an exponent, that they are inverses of roots. So in that sense, an exponent can be canceled out by the appropriate root. Okay, so that's one idea that we want to think about here as we sort of trudge our way through this equation. So first, as with solving most equations, we usually want to get this variable term that has the exponent attached to it. We want to get that by itself. In other words, we might say we want to isolate that variable term. So if there are any other uh, terms like this constant, this -1 here, let's go ahead and just move it over to the other side of the equation, right? That's not something crazy. That's something that we've been doing since the beginning of this course. So I'm going to add 1 to both sides. I don't know why I was getting ready to add 2. We're going to add 1 to both sides of our equation so that the 1's cancel out, and now I have x to the third power is equal to +1. Okay. And here's where we're going to make use of this idea here, this key idea that this exponent, a third power, can be canceled out by the appropriate root. Because if we have x to the third power equals 1, then the power that we're going to want to use, I'm sorry, the root that we're going to want to use to cancel out that third power is the third root, since the index matches that exponent. And if we do that on one side of the equation, we have to do it to the other side. So since we know that the third root and the third power are inverses of each other, we can say they cancel each other out, and we'll get x is equal to whatever the third root of 1 simplifies to. Okay, so there's a couple of ways you could think of it. The hard way to think about it, maybe the sort of brain teaser, is to think about what number could I multiply by itself 3 times to get 1? Well, that would be 1. Okay. The easy way to do this is to simply simplify it in your calculator. So remember, we can go get a third root if we just press the math button, and then go down to the fourth option, which is the third root, and then take the third root of 1, and that gives us 1. Okay. So you can see that even though we had this higher order polynomial equation with some really simple steps that are reminiscent of things that we've done in previous equations, we can pretty easily solve this equation. X is equal to 1. Okay. And if you wanted to check yourself, which I always highly recommend, you can do a little check to make sure that you got the correct answer. We will take our equation x to the third power minus 1, and that should equal 0 if we plug this in. So if we're checking, then we would have our solution, which is 1, raised to the third power minus 1, and then that should give us 0. So if we double check that, certainly 1 to the third power is 1, minus 1, and that's definitely 0 is equal to 0. So that's a true statement. So we know that our solution set does contain 1. Okay, so we only have one solution in that particular problem, and that's okay. We'll see that there's this idea with higher order polynomial equations that the degree of the polynomial, that highest exponent that's attached to the variable x, will tell you at most how many possible solutions you might end up with. Okay, so for this cubic, we could have ended up with 3 solutions. But right now, we're just going to say we only found one real solution, and that's good enough for our purposes. Okay. In higher level mathematics classes, there may be some other sort of hidden solutions, but we're just going to be looking for some of these real solutions. So if this makes sense to you, then that should be good. We don't want to really dig any more deeply into this than we have to. Okay. Let's take a look at the next example. Okay. So this equation says solve x to the third power minus 2x squared plus 3x minus 6 equals 0. Okay, and that's kind of a lot of terms here. So there are a couple of details that we want to sort of pay mind to, and that is one, this is a cubic or a third degree polynomial. And because that's a third degree polynomial, we may have at most 3 solutions here. In the previous problem, we only found 1, and that's okay. But at most, we may find 3 solutions. Okay. So you could think of it as 3 or fewer solutions. The other thing that you might notice is that if you pay attention to the left-hand side of this equation, we have 1, 2, 3, 4 terms. 4 terms on the left-hand side of the equation. Okay. And that should sort of maybe prime your brain or maybe jog your memory a little bit, because one of the primary methods that we're going to use to solve higher order polynomial equations, and I'm just going to rewrite the equation here, but one of the methods we're going to use to solve this equation is simply to factor and then use the zero product property. Okay. So if I have a 4-term polynomial equation, like I do here, then that should remind me that I can use factoring by grouping. So let's take a look at this problem when I group the first 2 terms together and the second 2 terms together. If I group the first 2 terms together and I factor out their greatest common factor, they have a greatest common factor of x. Actually, it's x squared. Almost forgot that. Okay, so x squared is the most terms or most factors that we can pull out of each of those terms. Okay, so what we will have left over if we factor that out is that we should have x squared times an x gets us back to the x to the third power, and x squared looks like we need a minus 2 here so that that distributive property kind of gets us back to that negative 2x squared. Okay. Then this first term on the next set or the next pair of terms is a positive. So we're going to factor out the positive GCF, and 3x and negative 6 have a positive 3 in common. So let's go ahead and factor out a positive 3, and then open up some parentheses. So it should be clear that 3 times x will give you the 3x back, and then 3 times, we need a negative 2 here to multiply these two together, the 3 and the negative 2, to give us the negative 6 back. Okay? And that's really nice because now the stuff that we have in parentheses is exactly the same. So that's going to be our next greatest common factor. We're going to factor out that binomial. And then the other factor that we're going to put in parentheses is x squared plus 3. Okay. So this is very similar to when we were solving other quadratic equations that had 4 terms. Remember that 4 terms should sort of signal to you that you're going to do factoring by grouping. Okay. And these two factors are equal to 0 because we are solving an equation after all. Okay. So once we have our polynomial factored, if it's set equal to 0, which is the whole reason why we want to get our polynomial in standard form, we can apply the zero product property, which is that simple idea. Remember, if we have A times B and that product that we get is a 0, that means that either A is equal to 0 or B is equal to 0 or possibly both. So that very simple idea is what allows us to say, hey, let's just take this guy over here, x minus 2, set it equal to 0, and then see what solutions we get when we solve that equation, that linear equation. Okay. So to solve that linear equation, we'll just add 2 to both sides of the equation. Certainly the negative 2 and the positive 2 cancel out, so we have x is equal to 2, and that is one of our solutions, x equals 2. Okay. But we said that we may have at most 3 solutions. So let's take a look at that other factor here and see how we might go about solving that. So we're going to set x squared plus 3 equal to 0. But this equation that we've now set up has a power of 2 on that variable. That tells me that this is a quadratic equation, so we should have 2 solutions. Okay, so just keep that in mind. Because we only have the squared term and a constant, that should signal to me that I'm going to use the square root property. But before I can do that, I need to isolate the square. So I'm going to subtract the 3 over to the other side of the equation. So now I have x squared is equal to negative 3. And then only when the squared term is isolated can I go ahead and take the square root of both sides. We know that the square root cancels out the square since those are inverses. We should have x is equal to plus or minus. That's going to give me my 2 solutions. And then the square root of negative 3 will just simply be the square root of 3. And since we're taking the square root of a negative, we'll have an I. Okay. So that is going to represent our 2 other solutions. So indeed, in this cubic equation, right, this degree 3 polynomial equation, we do have 3 solutions. So our solution set, if we write it all out, contains 2 and positive 3, positive square root of 3i and negative square root of 3i. Okay, not too bad. This is really just building up all the things that we've been learning up to this point, right? Because factoring is going to be fundamental. We saw it really on test 2 or module 2. But remember, we factor polynomials so that we can break them into smaller, simpler factors. Some of those factors may result in linear equations, like this linear factor here. But other factors may result in quadratic factors, which requires us to solve a quadratic equation. Again, really building off of the stuff that we saw in Module 1 and Module 2. Okay, let's take a look at the next example. Here we have another cubic equation, right? X to the third power tells us that we're going to have 3 max solutions, right? That's one idea here. And then we can count how many terms do we have in this polynomial. So it's already set equal to 0. We have 1, 2, 3, 4 terms. So we have 4 terms. So we want to kind of keep track of that, of those two details, because they are going to be important for us checking ourselves and doing just a little bit of reflection to make sure that we are on the right track. So we have x to the third power plus 3x squared minus x minus 3 equals 0. Just rewriting that problem so that I don't sort of write over the original. But since we have 4 terms, we want to factor by grouping. Let me use a blue pen here. Factor by grouping. So let's look at the first 2 terms and say, what is their greatest common factor? Here we have a common factor of x squared yet again. So I'll factor that out. And if I do that correctly, I should have an x plus 3 this time. Okay. Then the next 2 terms are negative. So I want to factor out a negative since that first term here, the negative x, is a negative, and they don't seem to have any number that divides into them evenly other than 1. So if they don't have a greatest common factor that's very obvious, you might factor out a 1 and see if that's going to help us out. So we open up our parentheses, and then we can ask ourselves negative 1 times what gives you negative x? And that's just going to be an x. Negative 1 times what gives you a negative 3? Well, it has to be a positive 3 since a negative times a positive gets you back to negative. Okay. And that works out nicely because the things that we have, the terms that we have in the parentheses here, are the same. So we have a common binomial factor, x plus 3, and then we have x squared minus 1 as our quadratic factor over here. Okay. So if you are kind of sharp, if you notice that this factor, unlike the quadratic factor that we had in the previous problem, is further factorable, then we can say, oh, we're actually not done factoring because this second set of parentheses, we can use the difference of squares formula to factor this binomial. Remember, if we have something of the form a squared minus b squared, then that will always factor into a plus b times a minus b. So really, the full factorization that we're looking for is x plus 3, and then we have x plus 1 and x minus 1. Since x times x will give us the x squared, and the 1 times the negative 1 does give us back that negative 1. Okay. So that's just a quick and dirty way of checking to make sure that you did factor that correctly so that we don't have to go through the full foiling process. There would be some extra terms in there that would cancel out, but we're trying to keep this nice and really short and sweet. Okay, so like I said, we had 4 terms at the beginning of this. We factored by grouping. There was a little bit more factorization to do here. Was that an absolutely necessary thing? No, we could have gone straight into the zero product property here if we wanted to, but I think it's really nice if we remember all of our factoring methods, get a little bit of practice with that difference of squares formula because it will make this next part pretty easy. So all 3 of these factors are set equal to 0 since they are the factor representation of the original equation. Okay. But now, using the zero product property, we can break this up into 3 linear equations. So the first equation is x plus 3 equals 0. The second equation is x plus 1 equals 0. And then this last equation is x minus 1 equals 0. 3 little linear equations because we have 3 factors that made up this qubit. Okay, and these should be pretty straightforward to solve. We can subtract 3 here. That gives us x is equal to negative 3. We can subtract a 1 here to cancel out that positive 1, so we get x is equal to negative 1. And then we can add a 1 here to cancel out that negative 1 and say x is equal to positive 1. Okay. So our solution set, if we were to write them all out, solution set includes negative 3, -1, and +1. Okay? And we have our three solutions like we anticipated when we started this problem. Okay? So if you feel like that's going a little bit fast, really just pause the video and maybe go back over that problem. But we are really simply applying some ideas that we have already encountered for module 2 here. Okay, just a little bit extra stuff that we have to watch out for, like the degree of the polynomial and the number of solutions. Most of the time, you will have three solutions when you're dealing with the cubic, but that's not always the case. So it's always a good idea to check your solutions by plugging them back into the original equation. So if we, for instance, plugged a -3 in here, here, and here, wherever the x's appear in the original equation, we should get 0 when we evaluate that statement. Okay, and that should be the case for checking all of the solutions. Okay, we're not going to do that just in the interest of time, but I implore you to check it yourself if you're feeling a little bit anxious and not sure and want that extra validation. Okay? All right. Let's take a look at a couple more examples so we can finish up this video. Now, we are going to encounter some degree 4 polynomials here. And most of the time, we're going to look at degree 4 polynomials that are called quadratic in form. Okay, so let's make some notes here real quick. So first, this is a degree 4 equation, which means that we may have up to 4 solutions, and that's max. There could be fewer. Okay. We might notice that the equation seems to be in standard form. However, instead of having x squared plus, something x plus something else, we have x to the fourth power plus 6x squared. So this kind of looks like a quadratic equation. Kind of looks like a quadratic trinomial since there are 3 terms. But the reason why this is called quadratic in form is because it kind of looks like a quadratic equation, right? Quadratic equations look like ax squared plus bx plus c equals 0, where we have x to the second power, and then the next term is half of this first term's power. So this is x to the second, and then x to the 1 power, and then we have a constant. Well, we have x to the fourth power, and then half of 4 would be 2. That's the next power on this variable term. And then we just have a constant. So that's kind of why it looks like a quadratic. Okay. In any case, however you want to call it, we're going to approach this similar to the way we approached quadratic trinomials. And that is, if we have 3 terms, that should sort of be jogging your memory a little bit, because a 3-term polynomial can be factored using the AC method. Now remember, the AC method is just our way of sort of breaking up this middle term so that we can get back to factoring by grouping. But once we do that, it should be kind of a downhill process because it should feel kind of familiar. Okay? So first we might label our coefficients. For the first term, the coefficient is a 1 because there's an understood 1 in front of the x to the fourth power. Our coefficient b is going to be 6, and our constant is 8. So to start the AC method, we're going to do a times c, which is 1 times 8, and we know that that's equal to 8. We'll drop right into a prime factor, not a prime factor tree, always do that. This is a factor t-chart, so we need all the factor pairs that multiply and make 8, like 1 and 8, 2 and 4, 3 doesn't work, and then we're back at 4. And we want to select the factor pair that will multiply to give us the 8, but we want those to add to give us the value of b, which is 6. And so the only factor pair that's going to work here is 2 and 4. And if those are both positive, then that's going to work out for us because 2 plus 4 is equal to 6, and 2 times 4 is equal to the positive 8 that we have here. So both of those conditions are met, which means we can rewrite our problem as x to the fourth power. Now we're going to use our factors here, plus 2, and watch out for this, since the middle term is an x squared term, we are going to call these two middle terms 2x squared and plus 4x squared. They have to have the same variable um, as this middle term that we're breaking up. In other words, they should combine or recombine back to make this middle term, which was originally 6x squared. And that's why they need to be x squares and not just x's like when we were solving quadratic equation. Okay. If you're okay with that, though, pretty much everything proceeds the same way as when we solved quadratic equations. So we're going to take a look at the first two terms here, and we're going to begin our factoring by grouping. So these first two terms seem to have an x squared in common. I'm going to open up some parentheses there. And here, be very careful. We need another x squared in order to get the x to the fourth power back. And then we need to multiply a 2 to get the 2x squared back. And now that makes sense. Okay. When we look at the next two terms over here, they appear to have a common factor of a 4. So I'm going to pull a 4 out, open up some parentheses, and then I should have 4 times x squared to get back the 4x squared, and 4 times a positive 2 to get back that 8. Okay. I'm just going to put a little bit of a cloud bubble over here just to partition our scratch work. We don't want to get that mixed up with what we're doing over here on the left. Okay. But since the terms in the parentheses are the exact same, that means that our first binomial factor is x squared plus 2. And then the next binomial factor is x squared plus 4, the GCFs that we factored out from the previous step. Okay. Now, if you inspect these factors, they are quadratic factors. So you might ask yourself, can we factor them further? And the answer is no, because this is a binomial. Even though we have an x squared here, there's two issues. One, 2 is not a perfect square, so we don't want to use the difference of squares formula here. But also the difference of squares formula requires that we have a difference that is a subtraction sign here. So since we don't have that, we're not going to be able to use the difference of squares formula. Same issue is going on here. We have x squared, which is a perfect square, and 4 is a perfect square. However, to use that difference of squares formula, we need a minus sign, a subtraction symbol here. And since we don't have that, we cannot use the difference of squares formula to factor further. That's okay. We're going to bring back our equals 0 from the very beginning of the problem. And now we're going to simply apply the zero product property to see if we can solve these quadratic equations and see if they'll give up their two solutions. So x squared plus 2 is equal to 0. We can solve this equation by subtracting 2 to cancel out this 2. Now we'll have x squared is equal to negative 2. And once we've isolated our square, well, we can go ahead and take the square root of both sides, right? Use that square root property here. So I'm going to put apply square root property. Okay, so we know that the square root and the square are going to cancel each other out. That will leave us with x is equal to plus or minus. And then we know we can't take the square root of a negative, or at least we can't take the square root of a negative without bringing in our imaginary unit I. But also the square root of 2 is not a perfect square, so we're going to leave that as the square root of 2, and then make sure we have our I, our factor of the square root of negative 1 that we've rebranded as I. That needs to be a part of our answer, okay? And that's going to give up those two solutions. We have positive root 2I, and we have negative root 2I. So going back over here, if we set x squared plus 4 equal to 0, we can do a similar process and subtract 4 over to the other side of the equation, such that we now have x squared is equal to negative 4. And then pretty much the same thing, apply the square root property, take the square root of both sides. so that we can cancel out the square, and x is equal to plus or minus, and the square root of 4 would have been just 2, but because I'm taking the square root of a negative 4, I need to keep in mind that that's going to be 2i now, okay? So our completed solution set, we said, should have 4 solutions, and sure enough, we have 2 solutions here. You can think of it the long way of writing it, that would be negative root 2i, comma, positive root 2i, and we have negative 2i and positive 2i. A total of 4 solutions, which was foretold, right? When we sort of started this problem, we said it was a fourth degree equation, and sure enough, we did get a total of 4 solutions. Okay. So if that feels like a lot, just remind yourself that we're doing the exact same process as when we solved quadratic equations. It's just that we now have to watch out for, are we going to get more than 2 solutions? You may want to check your solutions, but in this case, since we have imaginary numbers, that's going to be a little bit harder to do. Um, all of the quartic, that is fourth degree polynomial equations that we're going to encounter in this class, um, you don't have to check your solutions. As long as you get 4, and as long as you carried out the process faithfully, didn't lose any negative signs, and did your factorization correctly, you should be okay. Okay. So this is going to be sort of a trust me bro situation. Just trust that if you have your 4 solutions, that's going to be your best bet for your answers. Okay. So go ahead and put that into the homework platform, see if you get a green check mark, and hopefully you do. If not, just go to Math World, get some help from the tutors, or shoot me a message, okay? And then I'll give you some feedback. All right, last example here. It's going to be straightforward. I'm going to try to pick up speed just since we saw one that was a little bit slower. I'm going to do a little bit less annotation, a little bit less commentary. So let's just dive right in. I'm going to rewrite the question: x to the 4th power plus 3x squared minus 18 equals 0. So remember, pause or slow this down if you need to, um, and maybe review the previous example. But we're going to go right into the AC method because I know I have 1, 2, 3 terms in this polynomial. And I know that a times c in this case is going to be a 1 times the negative 18, which gives me a negative 18. So I'm going to go straight into my factor table for 18. That's going to be 1 times 18, 2 times 9, 3 times 6. 4 doesn't work, 5 doesn't work, and then we're back at 6. So we have all of our factor pairs. We need to get the factor pair that's going to give us a positive 3x squared. But we need to meet these conditions, right? We need for those 2 numbers to multiply to give us the negative 18, and they also need to add to give us the positive 3. And the only thing that's going to work here is going to be the 6 and the 3, but we need a positive 6 and a negative 3. So that negative 3 plus 6 stays positive, and then a negative 3 times the 6 will become that negative 18 that we needed. So we met both of those conditions. We'll go back to our 3-term polynomial and now change it to a 4-term polynomial. This is x to the 4th minus 3x squared plus 6x squared, since these both have to take on that variable term here, x squared. And then we'll bring down the minus 18. We're going to kind of ignore the 0 for now until we're done with the factoring process. Now we will factor by grouping, and these first 2 terms seem to have an x squared in common. And then we need an x squared and a minus 3 in order for that distributive property to yield back these 2 original terms. Looking at the next pair of terms, it looks like 6x squared and negative 18 have a positive 6 in common. I'm going to pull out that positive 6. We need an x squared and we need a negative 3 in order to get back to these original terms that we had up there. Okay, but that's okay because x squared minus 3, That seems to be our first factor, and then x squared plus 6 is our second factor. So we have these two quadratic factors. We might take a pause here to ask ourselves, can we factor this using the difference of squares? Unfortunately, 3 is not a perfect square. And also we might ask, can I use the difference of squares formula here? But again, 6 is not a perfect square, nor is this a difference. This is a sum, so we can't use that formula. So we'll just instead bring back our 0 that we started with at the beginning of our equation, and then apply that zero product property to set up two little quadratic equations, and we'll handle them one at a time. Okay. So to solve this quadratic equation, we have to get the 3 over to the other side of this equation. So we'll just add 3 to both sides. X squared is equal to 3. And now that we have our squared term isolated, we can take the square root of both sides such that the square and square root cancel out. We should get x is equal to plus or minus, and this is just going to stay root 3. Staying root 3 because 3 is not a perfect square. It can't simplify any further, but also because we don't have a negative, we don't have to worry about an imaginary unit here. Okay. Next, we said, okay, well, positive and negative root 3, that's going to be our two solutions. But since this is a fourth degree polynomial, we need two more solutions. So we're going to go back to this factor, x squared plus 6, zero that out, and now start solving that quadratic equation. So we're going to subtract 6 from both sides, cancel out our 6's. We have x squared is equal to negative 6. And here you might notice we're about to take the square root of a negative number. So we can do that. We just have to remember to bring in our imaginary unit I. So the square root and the square operations cancel each other out. We should have x is equal to plus or minus so that we get our two solutions from this quadratic. And now the square root of 6 is not a perfect square, so we're going to leave that alone, but we know we just took the square root of a negative, so we need our imaginary unit I. Okay. And so our completed solution set with our four solutions contain, if we were to write this out the long way, negative the square root of 3, positive square root of 3, negative square root of 6i, and positive square root of 6i. And that's it. Okay. So if you need to pause the video there and sort of like inspect everything that's going on this page, please do so. But that's pretty much all that we need to see to prepare to solve some of these equations on our own in the homework platform. So there you have it. We solved some higher order polynomial equations. And just to put a little bow on this lecture, if that felt like a lot, again, review this video maybe a couple of times, following along, writing out the problem with me. But you'll see when you jump into the homework that you're going to encounter some very similar polynomial equations, and you're going to use the exact same techniques that I used here in this video to solve those. Okay? These are just techniques that we have been working on since the beginning of the semester, whether it's solving linear equations, or even in Module 2, when we started factoring polynomials, right? These techniques are so flexible and so handy for solving all sorts of problems in higher mathematics. We're just really getting a taste of the world of polynomials, but you should not have too much trouble with that if we're mastering our factoring techniques, if we know how to solve our quadratics, because you'll notice that these equations sort of decompose into simpler equations that we've already dealt with. Okay, so that's all I'll say here. I hope to see you guys in the tutoring lab if you're needing some assistance, and look forward to the next video. We're going to be working on polynomial functions and building on this material.